morning to the second day of our European Robotics Forum. I hope you have enjoyed the first day yesterday, also the welcome reception, and I guess also lots of you already attended the first workshop session. And yes, now it's really an honor to go for the keynote. I guess it's really the highlight of the ERF. We have Dieter Fox with us. We all know Dieter. He's one of the authors of the book Probabilistic Robotics, together with Sebastian Thurn and Wolfram Burkhardt. He's a German, and since 27 years you are in the US. Today, professor at the University of Washington, head of the robotics research at NVIDIA, and it has been last July in the RSS, the Robotic Science Systems, is a high-class conference. It was happening in Delft last summer, and there Dieter gave the plenary, and after the talk I went to him with a ERF mug and said, "Oh, Dieter, we really enjoyed your talk. Would you be eager to also give a keynote at ERF in Stuttgart in March?" And yes, finally, you have accepted. We are really excited about that. And yeah, thank you for coming here, and we are looking forward to your keynote. Thank you.
Thank you very much. Thanks a lot for the invitation, the kind introduction. Yeah, I'm obviously pretty cheap to get for a mug. Today I'll talk about where's Robot GPT, and as roboticists, that's one of the questions that on the one hand side I think nowadays we ask ourselves very often, like how far are we when we look at all this progress in these other areas, but it's also often a question that we get asked by others, right? Like, why haven't you actually solved all these problems yet? So this is a research-focused talk, so I'm going to try to give my perspective on some of the key aspects of that problem space. And I will start with just kind of providing some context on how I think the whole, let's say, space of robot manipulation and what we call generative AI kind of fits together. Caveat, so there's not too much disappointment here. I will virtually not talk about humanoid robots. I'll just talk about standard manipulation. But I think many of the aspects of what I'm touching upon here, they really apply to kind of this whole new space of humanoid robots as well. So first of all, I think we all agree that over the last few years, we've seen astonishing progress in large language model, large vision models. Think about GPT, ChatGPT, Gemini, all these different systems where we have these techniques that are trained on internet scale data and that have an astonishing understanding, some form of understanding of language, of reasoning, and also visual understanding, right? So nowadays they are extremely good at understanding the content of images, describing what's in images. Also, when you think about generative techniques, so for example, you can generate beautiful images, beautiful videos that also look actually like they are 3D content consistent. And the key ingredients that I think really made that possible is on the one hand side that there is vast amounts of training data, right? So these language models, they're not just trained based on random content or something like that, but they are trained on language content that is taken from, let's say, the internet typically, right? Very large amounts. But the text that is on the internet is not just random collection of words. It's written typically by humans with some kind of content in mind, which means the sequence of words is not just random sequences, but it's actually sequences that convey meaning. And these models, by being trained on that data, they can kind of learn to at least replicate this. The same also for images. These are not random collections of pixels, but they actually convey kind of imagery of the real world. So on the one hand side, these models, language and vision models, have the advantage that they can be trained on vast amounts of data. So we're talking about trillions of tokens or words that they are trained on. The next ingredient is the models themselves. These what we call nowadays often transformer models or diffusion kind of models that have the ability to digest that data and compress it in a form so that you can later query them and they come up with meaningful answers. And the third is really this notion on how they are trained, and this is kind of how we could connect it to robotics. I call it here behavior cloning, where the idea is that, for example, the language models, you take in a certain part of a text and then you just ask the model, what would the next word look like? And you can keep on repeating this, and then these models learn to predict future words, right? And by training that on these large data sets, these models are kind of forced to also kind of get some form of understanding of the underlying grammar and things like that, for instance. And then, of course, in addition to this pure, what we call behavior cloning, they also are then, of course, trained on specialized data sets, and reinforcement learning is becoming a more and more important topic. So why haven't we really seen that in robotics yet? I think there's two pieces here. On the one hand side, with what Hans Moravec, what people call Moravec's paradox, is this notion of that the things that we often believe that are difficult turn out to be very hard. So for example, for me to pick up this phone, turn it on and things like that, I don't even have to think about this, right? I just do this in a very automatic way, these kind of physical skills. And it turns out that that is something that is very, very difficult for computers and, of course, hardware to replicate. At the same time, the things that we always thought that are so hard, because we humans consider them to be so difficult, like playing chess and Go, those turn out to be not quite as difficult as we thought. So again, the key trick is that robotics is much harder than we thought it would be. So my hypothesis and the takeaway from these large models is actually that if we could generate the kind of data that these language and vision models are trained on, and kind of put it into a form that is kind of suitable for what I call behavior cloning, then I think we could actually train robot algorithm mechanisms that operate extremely well. I'm not saying that we're going to suddenly solve general AI or something like that, but I think we should get robots that are far more capable than the ones we see right now. And the key questions in this context is, where do we get the data from in order to train these kind of models? And then also another question I want to touch upon is, how can we leverage these pre-trained large vision and language models in order to improve the capabilities of our robots? So with respect to this behavior cloning, we've seen some recent really nice successes on, I'm sure many of you have seen these videos of, for example, humanoid robots doing some really cool stuff like putting things into a fridge and other kind of tasks in industrial settings. And typically how they are trained is that there's a human that teleoperates a robot to do a certain task, and the human teleoperates a robot to do the task, let's say, many times. And then they feed this data into one of these transformer algorithms, and the model then learns to replicate this task, right? So for example, images go in and control actions for the robot go out. And then if you do this often enough, you can then generate these actually very convincing and cool videos and behaviors for the robot. One big caveat so far is actually that I think many of these demonstrations are very limited, which means it's a very constrained setting. And if you change something, then often they might not quite work as anticipated. I just want to briefly give you here a real kind of academic example of what the problem really is with this whole behavior cloning and why data is so important. Let's assume we have our robot manipulator, and we want to teach it to pick up this red block. And we can do this in simulation. We can generate, for example, 1,000 examples of placing that block on that red patch. And then we can use these examples to train a transformer behavior cloning model. And then now on the right side, you can see this is now how the model actually learned to pick up this red block. So it looks like we're done. Now the robot can do this. And again, the one on the right side is the one that was trained. This is a model that is trained on the data on the left, similar to what you see with teleoperation and kind of things like that. Now the problem is, we as humans, when we see this, if I show you this robot picking up the red block, if I now show you this scene on the right, and I say, okay, now we want the robot to pick up the red block on this blue patch, a human would say, well, obviously, if it can pick it up on the red patch, why shouldn't it be able to pick it up on the blue patch? Now, if you run that same model on the data on the right, then we'll see that it suddenly has no idea what to do. Okay, because it's trained only on data that showed it on the red patch. Okay, so that's important to have in mind. So now one thing we can do is we can generate training data for all the patches. Okay, so now we need more data, but now since we have in the training data all this variability, we can actually now train a policy that actually succeeds on all 3 patches. Okay, because it has seen those kind of examples, right? And just have in mind that the positions of this block vary randomly, so it's a continuous space of blocks. So now we might say, well, this robot now finally it's good at picking up this red block, but then we're still having trouble, for example, if suddenly these patches are kind of elevated a little bit. If this policy that succeeds in the middle video, if I apply that policy in the setting on the right, suddenly it doesn't work anymore because it has never seen an elevated block. And the problem is we humans, when we see this example, we say, well, that's trivial. It's of course, it's kind of, we don't even think about that, right? But for these models, this is still a problem, right? Another example, same setting, all I'm changing is actually the color of the table, the texture. The same model fails, okay? So this is just, I just want to highlight the complexity of this problem space, right? That we often tend to think that, oh, these models can do all these things, but often it's much more constrained than you have in mind. So that is why it's so important, if you want to train these robots to succeed in open world settings, we need a lot of training data. Because we need to vary across all these different things, right? What the environment looks like, where the blocks are, how big they are, and all this kind of stuff. So where do we get the data from? There's 3 kinds of data we can leverage. On the one hand side, it's just the internet is full of videos, cooking videos. So you might say, if I can watch a person cooking, then we should be able to use it to teach robots. There's actually a lot of active research going on leveraging these kind of instruction videos. And I think this is very, very promising moving forward, just because of the amount of data. But at the same time, I think we have to admit that the gap between these videos and the actions that a robot should perform is still too large, which means you cannot just watch that video and then put it on your robot, what you learn, and then your robot can suddenly do that. So there's still a pretty big gap. The other one is real-world teleoperation, which is what I showed you on this previous slide, which is what many of these companies are currently pursuing. This is actually really high-quality data, and we're seeing very good results, but at the same time, it's just very, very expensive, very costly to scale that up. And the next data source is, of course, simulation. And this is something that we've been pursuing a lot, where the idea is if I can teach my robot in simulated environments where I can vary these things programmatically, then hopefully I can train it at a much larger scale than what I could achieve with, let's say, teleoperation. The key caveat here is what we call the sim-to-real gap, that things that the robot might learn in the simulator, the real world might look or looks different. And therefore, we need to make sure that these things that we learn in sim, that they transfer to the real world. So in the next section, I want to talk briefly about how we can train, for example, some manipulation capabilities in simulation. Imagine you want to teach a robot to pick up objects, to grasp objects, okay? What you see here on the left is, imagine in a simulator, in a physics simulator, you have a model of an object, like this red object here. And what you do is you just randomly guess positions for the gripper on how to pick up this object. Okay, let's assume you guess 1,000,000 times. We can do this in parallel on a GPU, so it's not too expensive. And for each guess, what I'm going to do is I'm going to go in my physics simulation. I'm going to say, close the gripper and shake. And if the object stays within the gripper, then that was a good grasp. And if it goes away, then it obviously wasn't a good grasp. So by doing this, let's say with 1,000,000 possible grasps, maybe 1,000 of them actually are good guesses. And then what I have is a data set of grasps that work well on that specific object. Okay? I can now scale this to data sets with more objects. Here what you see is a data set that's roughly 9,000 objects, and it's all annotated with grasp poses that work well on these objects based on a physics simulator. Okay, so they're kind of verified through the physics simulator. I can now use these objects, place them in simulated scenes, and I can teach now one of these transformer models to replicate these good graphs, which means the input is a scene, which means in this case actually a depth camera observation of the scene, and what the model generates is good ways for picking up the object. And it turns out that that actually works then pretty well in the real world. So here's a robot, for example, picking up some of these objects here out of a sink, different settings. Have in mind that this robot has before that never seen a real world object. This was all trained purely in simulation. Also have in mind that these objects are unknown, which means these specific object models were not in the training set of the robot. Okay? And how we achieve this is by just saying, if you teach it on 9,000 different objects in different settings, then there's so much variability that the network kind of needs to learn what it means to pick something up rather than memorizing the data set. Okay? You need to have enough variability in there. Also, another component here is actually the segmentation in these different pieces. They're also all trained in simulation through simulated rendered data. Another example here is, for instance, if you want to, for example, teach a robot to place items in a shelf or in a pantry or something like that. We can do this in the simulator by saying, okay, let's generate a scene. This is, for example, let's say a bookshelf, and these dots are little like 3D point cloud observations. The details don't really matter so much. But let's assume the blue is the book where we think it should fit. Okay? And again, in simulation, we can do this pretty easily. What we now do is actually we perturb the position of that book. Okay? We randomly kind of move it around. And this is what we call, we add noise to the system. And now what we're going to do is we're going to teach a neural network to undo that noise process, which means the neural network learns to go backwards from a noisy position of this book into a position that fits actually into the shelf. Okay? This is exactly the same process when you look at, some of you might have heard of Sora or this image generation network. They are trained the same way. They take the training data consists of an image. They add noise to that image, and then they train a network, a so-called diffusion process, to undo the noise and generate good-looking images. We do the same thing here, just for putting books into a shelf. Okay, but it's the same process that we see for these large models. And here you can see this kind of now this learned denoising process of the network, where we place these objects in a random position, and the network learned to kind of fit them, wiggle them into the place. Okay? And then we can use this as a target position for where to put it. And this actually transfers also pretty well to the real world. We can put this, for example, in real, like where there's space in the pantry to place it, which kind of can. It also works, for example, for placing. It's one of the tasks often for placing these mugs and hanging them there. Okay? Again, have in mind everything purely trained in simulation. Something that is actually, I think, more relevant here is the notion of assembly tasks, where it's not just about picking something up and placing it somewhere, but for example, in industrial assembly, often we have these what's called contact-rich tasks, which are like very fine-grained insertion tasks or threading a nut on a bolt. That's an area we also started looking at, and it turns out that simulating these interactions is very difficult. So at the time when we started this was kind of the best simulation that was out there for threading a nut onto a bolt, and the simulation itself was 350 times slower than real time, which kind of beats the purpose of simulation because you want to simulate things faster than in the real world. Okay? So we worked with the wizards at NVIDIA that know about fast simulation and all these things, and developed a new simulation system that was now able to actually, on a GPU, to simulate, in this case, 1,000 of these interactions in real time. So beforehand, it was a single one, 350 times slower than real time, and now we can do 1,000 in parallel in real time. The advantage is, once you can do that, we can now actually start learning in simulation to perform certain actions. There's this technique called, you might have heard of reinforcement learning. So we can now do reinforcement learning in the simulated environment and then perform these insertion tasks. So for example, here on the upper left, you can see some examples where on the upper left is simulated environments where we train a policy, And then next to it on the right side is the real world counterpart where we can now execute these policies in the real world. Again, train in sim and then transfer to the real world. Here's also just a more complex assembly task. I'll just go a bit faster through this one here. So it's kind of wiggling all these things into place. And at the end, it also puts even the nuts in there. I'm fully aware for the people from industry, this is not fast enough yet, but I think it's a very good first step that we are getting there to being able to train these things in simulation. We're also looking at, for example, simulating tactile sensing. This is kind of a shell side simulation, so we can simulate tactile sensing on the robot gripper, and we can train policies that leverage that, and they also transfer to the real world. Now, all these different pieces of how we can leverage simulation data and use it to generate more data are also, of course, making it more and more into kind of NVIDIA-style products, right? And where it's about workflows and tools that the community can use to train their own robots. And this is now the one connection to the humanoids. This is from Jensen's presentation at CES. This is one section.
Developers around the world are building the next wave of physical, AI-embodied robots, humanoids. Developing general-purpose robot models requires massive amounts of real-world data, which is costly to capture and curate. NVIDIA Isaac GR00T helps tackle these challenges, providing humanoid robot developers with 4 things: robot foundation models, data pipelines, simulation frameworks, and a Thor robotics computer. The NVIDIA Isaac GR00T blueprint for synthetic motion generation is a simulation workflow for imitation learning, developers to generate exponentially large data sets from a small number of human demonstrations. First, GR00T Teleop enables skilled human workers to portal into a digital twin of their robot using the Apple Vision Pro. This means operators can capture data even without a physical robot, and they can operate the robot in a risk-free environment, eliminating the chance of physical damage or wear and tear. To teach a robot a single task, operators capture motion trajectories through a handful of teleoperated demonstrations, then use GR00T Mimic to multiply these trajectories into a much larger dataset. Next, they use GR00T Gen, built on Omniverse and Cosmos for domain randomization and 3D to real upscaling, generating an exponentially larger dataset. The Omniverse and Cosmos multiverse simulation engine provides a massively scaled dataset to train the robot policy. Once the policy is trained, developers can perform software-in-the-loop testing and validation in Isaac Sim before deploying to the real robot. The age of general robotics is arriving, powered by NVIDIA Isaac GR00T.
All right. So as you can see, this is where these ideas go when we're talking about using simulation to generate the kind of amounts of data that we need to replicate and to multiply the demonstrations that we get through teleoperation. And this is, of course, applicable to both humanoid-style robots, but also industrial manipulators. In the remaining section, I want to actually talk about how we can connect this to these large vision language models that we're seeing out there that are kind of independent of robotics. Because so far I talked about more or less individual skills, right? Like what a robot can do with interacting, but we haven't talked about these large models. So this is some very recent work that we've done in the research team. And it seems like now various of the efforts are converging on what we might call hierarchical action models for this, where we say, let's assume we have as input text and an image that describes what the robot should do, for example. And then the vision language models, they are really good at analyzing text and analyzing images, but they're not so good at actually talking about specific robot control actions, right? So what we are trying to do is we're trying to teach these models, these high-level models, instead of generating immediate robot controls, what they are generating is kind of the guidance that we can give into a lower level policy so that the lower level policy actually needs to figure out how to do the controls, and the high level can stay at something that is a bit more abstract. I'll give you an example moving forward. So the specific model we used here, details don't matter too much, is VLA, which is an open model, which allows you to fine-tune it. But it's one of these, imagine these GPT-style, very large models that are pre-trained on internet-scale data. And what we're doing is we fine-tune it on more specific robotics tasks. And what we teach the model to do is to say, it should generate a trajectory sketch on where we think the robot gripper should move in order to execute a certain task. And that sketch is then fed into a low-level 3D policy that then hopefully executes it in 3D. So here how this works, for instance. Let's assume we have this picture here, and the task is put M on Mona Lisa, right? So we look at this, and we can clearly see what's meant is the block with the M on it, right? And the picture of Mona Lisa. The problem is we might have never trained it on that specific task, of course, right? So first what we do is we feed this into one of these large vision language models, and the VLM outputs as answer pixel coordinates in the image. So for example, it says this blue circle that you can see here in the image would be the first coordinate and said, this is a place where you want to close the gripper, then move to this location, for example, and finally move over here to Mona Lisa and open the gripper. We can now turn this into a full, let's say, 2D trajectory. And the colors on the trajectory, they indicate kind of the timeline along the trajectory. And we can now take that as input to a lower level policy that should then actually execute it. And to make it easier for the lower level policy, we also add depth camera information so that it's not just a 2D image, but it's a point cloud that the policy can operate on. And the text input for this policy is also not put M on Mona Lisa, but a more generic task like pick up an object and place it somewhere. So the lower level model takes that as input, and its role is now to generate actually the 3D motion itself, right? So we have these two levels. The high level generates the trajectory, and it understands the semantics and things like that. The low level model then executes. In the interest of time, I'm going to skip how we train that, but we can train that actually from pre-generated data sets like this one, where the task here would be move the green object in the silver bowl, and then it generates a 2D trajectory like this. This is just the training data that is used for this high-level model. We can also use simulation data for this, for example, how to open a drawer and things like that, or press buttons, and we can then generate these kind of desired outputs for the model. And here, let me just give you 2-3 examples what this high-level model is then actually capable of, for instance. So this is, I think, a pretty interesting one is where you see the scene and the task is move the S to the place the arrow is pointing at. So this is actually not trivial, right? If you would have to program that, it would not be easy to do, but the model automatically sees, oh, there's an arrow over here, and the arrow is pointing, obviously, at the red plate, right? Interestingly, for example, if we give it the same image and we say, move it to the plate the arrow is not pointing at, the model correctly points it at the green plate, right? And this is the kind of reasoning that we want from these large vision language models, right? This kind of open world understanding. Let me give you another example. This is an example that we used in the training data to fine-tune this model. Here's, for example, screw the light bulb in the lamp. But you can see that visually, this is clearly simulation, right? It doesn't look anywhere realistic. But later on, when the model is trained, it can actually generate that trajectory on a real-world image, right? Because the model is trained on a combination of simulated and real-world data. Another example, in the training data, there was something like push the button with the color orange. And then later, we can give it a real-world scene with real buttons. And the model is even able to recognize the big red button because there's 2 red buttons. And instead of saying the color green, here in this case, we just say with the color of leaf. And the model automatically just recognizes, oh, it's got to be the green button. Okay, so this is kind of the capabilities that we're getting from these large models. Now I just want to give you some examples of what we can do now with the complete model, which means a combination of the high-level and the low-level execution model. So like these towel tasks that we often see, In the lower left, we can do tasks like wiping or putting objects in a shelf. The middle one in the upper part is interesting, so because the model understands Chinese, so it can do any language, of course, because that's what you get through these large language models, right? And again, the key trick is really that these models inherit these open world capabilities that we see from techniques like GPT or Gemini or other kind of models. Here's one more example, the last one. Is then, for example, here, where you might say you put these on the table, and then you can even have kind of a conversation with the model where you say, what's on the table, which trash bin do they belong to, and it recognizes there's a crushed can, a water bottle, crumpled paper, and based on this general reasoning, it also knows which one should be the recycle bin, which one should be trash. I guess that also depends on which country you're in. But then you might just say, okay, pick up a crushed can and put it in the recycle bin, and then the model is actually able to execute that, right? Again, because it has this combination of the high-level reasoning and the low-level execution model. And for the roboticists here again, I think the key limitation that we observed, not surprisingly, is still the low-level execution, of course, right? I want to be very honest about this, that there's still a lot of effort that has to go into this. With that, I want to come to my conclusion is where, on the one hand side, I think we all agree, again, that these language and vision models have truly outstanding capabilities in analyzing input data, understanding it, performing some kind of reasoning. We can have a long discussion about how limited the reasoning, of course, is, and that these problems aren't truly solved yet. But it is still, I think, extremely capable, right? At the same way, we're still not quite there with a robot GPT version of that, right? Where you just tell your robot what it should do, and it really knows what it should be doing. I believe that simulation can play a really, really important role in scaling the training of these models so that we can actually at least get closer to the capabilities that we would like to see from a robot GPT kind of model. There's the many advantages to the simulation. We can, again, have that in a discussion afterwards. There's also the aspect of benchmarking. How do you test and benchmark and compare different models, for which simulation can be, I think, extremely useful. And because simulation is cheap, we can involve a much broader community in doing this rather than requiring everybody to buy their relatively expensive hardware. And I think what I showed in the second part, especially these hierarchical models that kind of combine the open world reasoning that we're getting from these pre-trained models, if we can fine-tune them on robot tasks, which I showed you we can do from not too much data, and then we combine them with lower level reactive policies, then I think we will soon see some very, very capable robotic systems. And with that, I'll thank you for your attention. And thank, of course, all the researchers and also the university collaborators and grad students that were involved in the work, and many of the interns. Thank you.
Thank you. Yeah, thank you, Dieter. It was really impressive. And also regarding last summer, again, we saw further developments, especially in the reasoning area. And we have also allowed some questions from the auditorium. I guess it's okay to use the coffee break for that. But I have one question, as we have also lots of robot manufacturer component suppliers like gripper, cameras here in the auditorium. Where do you see limits on the component level? Also, or the other way around, what are your wishes regarding robots, grippers, cameras to make it happen? Or what would make your life easier?
Yeah, that's such a good question. And we also had discussion outside already. There's a question, for what can you use suction cup, for which can you use grippers, dexterous hands. I think on the one hand side, it's very exciting, the progress we see with the developments on the humanoid robots, right? Where we still have to see how easily it will be to deploy them, let's say, in industrial setting. But I think the fact that there's so much funding going into this domain is great for robotics, right? And I think, of course, more dexterous capable manipulators would be, I think, is something that we're really craving for. And I think touch sensing, right? Like getting tactile sensing onto these hands so that we can have these robots to do much more fine-grained interaction, I think is going to be very useful. The problem is at this point that most of these touch sensors, they only cover like very small sections of the fingers, for example, and all the problems with like cabling, routing, and all of that is still very hard.
Great, thank you. Yeah, I guess we have to also check Resense. They are outside for tactile sensors later on. So are there questions from you? And we have, the mic is in the floor. Also you have to stand up and go there, please.
Okay, can we just ask? Yeah, thanks for the great talk. So I have a question to the last part, to the hierarchical approach, and in particular to the latency of the first part of the processing when you analyze the scene. If the scene is dynamic and the objects are moving, and they take time to make that analysis, and the analysis might change the motion. So I wonder if we fall back here to the classical sense, plan, act paradigm, where sense and plan was always too slow for the act, and how do we deal with that? I
think that's a great question. That is actually at the beginning also that partly motivated us to do this hierarchical approach, because the high level and the low level, they don't have to run in sequence, they can run in parallel, right? The high level can constantly, let's say, analyze the imagery data, let's assume at 5 to 10 hertz or something like that. And then the low level policy, we can train that to take the most recent, let's say, guidance from the high level, and it can run at, I'm not saying at 1,000 hertz, maybe you need another controller, of course, underneath that, but I think that policy can run at a much higher frequency than the high level. So I think this kind of hierarchical approach at least helps with that. The other piece is also that, of course, in this version that I showed, it was really like show the image and then run the high-level model to come up with the trajectory, but you can run this also kind of in a closed loop fashion, right, where this trajectory is regenerated over and over again. And another thing I want to highlight is that this idea of the 2D trajectory is kind of, I must say, is kind of a crutch, meaning it's a first attempt of making this connection between high and low level. I think ultimately it should all be kind of trained interfaces that we learn from data. So it should be, if you think about language models, it should just be tokens that are exchanged between the high level and the low level model. But that requires more research, and we're starting to look into that.
Okay, thank you. And one more question.
Yeah, I have a question to the generation of training data in simulation. If you consider a robot, the behavior, how a robot, for example, gets into contact depends on internal control, weight of the robot, and so on and so on. How do you integrate this specific behavior into your training data?
Yeah, that's a great question. I can point you, actually, there were some specific papers we did on that when I briefly talked about this industrial style insertion kind of task. And there it is exactly about this kind of fine-grained contact models. And we have some work also where, for example, we simulate actually also the force feedback that we might get through the joints, for instance. And we are able to train a policy. So the simulator generates these force feedbacks artificially, and we can train a policy now that actually transfers to the real robot system, even though it's trained on that, right? But this is not an, I would say, out-of-the-box experience. You still need to know something about the target controller. But ultimately, this is where we want to go, right? Where you would like to be is, let's say, you train it in sim, and literally that policy should run on your robot with the caveat that, of course, the low-level controller is still one level below that. Okay. So I think we're making very promising project on that. If you want to continue, I can point you at some research papers.
Thank you. Great. Dieter, thank you for this excellent, insightful talk. Impressive. It's really thanks. So we have something for the mug. Some German from Stuttgart.
Awesome.
Thank you.
Thank you.
And for the others, thank you. We have one special guest with us. I wanted to shortly introduce. Professor Schraft is with us. And I guess without him, we would not be here today. So he was head of IPA from 1993 to 2007. He started the robotics in the early 70s, and he's the Mr. Robot known as Mr. Robot here in Stuttgart, also Engelberger Award. Mr. Schraft, thank you for joining us today.